This video lesson corresponds with the first half of Chapter 17 on equilibrium and kinetics. We're going to start with our study of kinetics, which is the study of reaction rates. And in particular, we're going to look at collision theory. Now, collision theory is the idea that chemical reactions occur when particles collide. Particles meaning atoms or molecules. And you need to get those things, atoms and molecules in a reaction, close enough to each other to react in the first place. And to do that, they need to collide or come close to each other. However, they must have enough energy in that collision to cause the reaction to proceed. If they do collide, some atoms and molecules at a low energy, the reaction won't proceed. So the study of reaction rates is called kinetics. And the first question we should examine in our reaction rates is, are there some things we can do to change the reaction rates, to speed them up or even to slow them down? And the answer is, of course, there are several things we can do. First of which is probably most obvious, is change the temperature. If we increase the temperature, you do a number of things. But from a particle theory standpoint, you increase the energy of those molecules or atoms, and therefore you increase the number of collisions. You do two things. You don't just increase the number of collisions, you increase the energy per collision. So we'll talk about that in a little more detail now. There's a thing called an activation energy, and the activation energy is the minimum amount of energy you need in a collision between atoms or molecules for the reaction to go forward. If you don't collide with enough energy, the reaction does not go forward. So activation energy. The symbol for it is E sub A, the energy of activation. We're going to look at the way that activation energy corresponds with collision energy with respect to this reaction right here, which are two bromonitrate gas molecules that collide and form bromine gas, and two nitrogen monoxide molecules. So we can envision it as something like this. Here's the bromonitrate molecules that collide. When they get close enough and the energy of collision is great enough, we will cause some bonds to break, those between the nitrogen and the bromines, and some new bonds to form between the two bromine atoms. So we form multiple new compounds. Now, the activation energy for that collision and that reaction can be depicted in something called an energy diagram. And an energy diagram shows the energy content of a reaction as the reaction proceeds. I think we've done this a little bit, but let's take a look at what I mean by that. Down here is a reaction diagram for this reaction. Two bromonitrate gas molecules that collide and form two nitrogen monoxide and a bromine gas molecule. This energy hill right here is what's called the, let's look at the axes of this graph. On the left, going from low to high, is energy. What is the energy content of the reactants versus the products? And this is the reaction progress. And essentially you can think of this as the progress of the reaction over time. So notice that there's an energy barrier here. This is called the activation energy. If the two particles don't collide with enough energy to get over this barrier, the minimum amount of energy you need to have a reaction go forward, then the reaction doesn't occur. And this is called the activation energy. Now, there's some things to notice, to pick up on in this diagram. First of all, look at the energy content of the reactants shown here with this line versus the energy content of the products shown here with that line right there. And I want you to, poorly drawn line, but I want you to notice that there is a difference between the two. The reactants have a higher energy content than the products, and that's shown right here. That amount of energy must be released by the reaction. So this is an exothermic reaction. And once again, the products have a lower energy content than the reactants, so energy must be released. Up here is a very strange and kind of unusual state of matter, which is called the activated complex. And the activated complex is a state of matter that is between reactants and products, kind of shown here. The the bonds between the bromine and the nitrogen in the bromonitrate are in the process of breaking, and new bonds between the bromines are in the process of forming. So it's a highly unstable, highly energetic state of matter. And then energy is rapidly released when new bonds are formed between the product molecules. You can think of activation energy right here, this amount, well, I'm sorry, let's undo that. The activation energy is this amount of energy right here, okay? From energy content of the reactants to the, let's say, the maximum point of the energy barrier. That's the activation energy. You can think of it as putt-putt golf. Yeah, let's say you had this obstacle or barrier to get over in order to sink the ball. If you don't collide with the ball with enough energy, you don't get over the energy barrier, and there's no way you make a product, which is the ball sinking into the cup. So the activation energy is, in this case, that amount of energy that you would have to add to the molecules colliding in order to get over that energy barrier and proceed to products. Other things that can change the reaction rate. Concentration. Now, concentration, or pressure in the case of gas, is simply how many molecules, reactive molecules, are there present per unit space. And obviously, the higher the concentration, the more molecules there are, and the more likelihood of a favorable collision to make the reaction go forward. Let's see, what else? Particle size or surface area. Now, this is a hard one to envision, but a small particle size corresponds with a high surface area, which means a higher reaction rate because there are more areas available for collision. Now, let me show you what I mean. Let's take an example of, let's say, a sugar cube. And this sugar cube is 2 centimeters on an axis, on a side, and therefore 2 by 2 square, one face is 4 square centimeters. And this, of course, is a cube which has 6 sides, and so 6 times the 4 square centimeters is 24 square centimeters of exposed area on the face of this cube. The volume, of course, is length times width times height, right? And 2 times 2 times 2 will be 8 cubic centimeters. Now, let's take this cube and let's cut it into 4 equal cubes. So we're going to have a knife of some sort that can chop this cube into, in other words, half each side. Now we've got a whole bunch of cubes that are a lot smaller, but they are 1 centimeter on a side, and therefore each face is 1 square centimeter, length times width. And you've got 6 of them. So each cube here has a surface area of 6 cubic centimeters, right? Each one is 6 cubic centimeters. Sorry, square centimeters, my bad, area. And now we have 8 of them. So 8 times 6 is 48 square centimeters of surface area. So what we have done here is we have halved the particle size, at least from an area standpoint, from 2 centimeters on a side to 1 centimeter on a side, and we have doubled the surface area at the same time. The volume has remained identical. So with all these available new surfaces for chemical attack or for collisions to occur, the reaction rate will increase. And in this case, the reaction rate will double because the surface area has doubled. So that's how it works, and I will show you this in person the next time we have class. Now, what else can make a reaction go faster? From biology, you may remember a certain class of biochemical compounds called catalysts. In biochemical terms, they're called enzymes. And enzymes work as follows. They usually will speed up the reaction rate, and they do that by decreasing the energy barrier, the activation energy. So most catalysts will temporarily bind to a reactant, and the way it lowers activation energy is by orienting the reactant molecule in a way that best allow favorable collisions to occur and the reaction to go forward. So therefore, more particles are likely to collide with that enzyme substrate complex in a favorable way. and make the reaction go forward. And therefore, less energy is consumed in the process. Now, remember, the catalysts are not consumed. They are recycled and used again. And that's the beauty of enzymes, is they can be used over and over in biologic systems. So here's the cartoon you may be used to, where you see a lock and key model of a substrate versus an enzyme. And the enzyme essentially orients the molecule such that it makes this decomposition reaction occur more easily. Here's an energy diagram of the same thing, and notice that we have lowered the activation energy. In the catalyzed state, the catalyzed is shown here in blue. And so by doing so, there's going to be more molecules that have that minimum energy to get over the hump, because the barrier is smaller. That's all. So that's the idea behind kinetics. Let's move into a discussion of equilibrium, because it will reference collisions and kinetics as well. So equilibrium is a balancing of processes. We learned in chapter 16 that reactions can have both a forward and a reverse direction. We learned this especially with respect to acid and bases, conjugate acid bases in the Bronsted-Lowry model. So equilibrium is a special case where the rate of the forward reaction, shown here, is equal to the rate of the reverse reaction. Now there's some special things that fall out of this idea that equilibrium is not a balancing of mass on the product versus reactant side, but it's a rate expression. A forward rate equals the reverse rate. So let me show you what I mean. One of the things that falls out, let's talk about this first, is that there's no change in concentration over time. And equilibrium conditions usually occur in special scenarios like closed containers. Open containers, like open systems, are not good for setting up equilibrium. It's pretty rare. So here's an example. Let me do this. So let's take water in a Erlenmeyer flask, and let's pretend it's a complete vacuum above the water, and let's stopper it and just let the water evaporate. Early time, the reaction is going in just one direction. The water molecules are coming out of solution into the gas phase. But as the reaction proceeds over time, the concentration of gas phase molecules begins to increase, and therefore there will be some collisions back into aqueous water, and some of those molecules will go back into the aqueous phase. And this keeps going and eventually sets up a condition where you've got just as many molecules coming out of solution into the into the gas phase as you do having molecules collide with the aqueous phase and go back from being a gas into the aqueous phase. This is equilibrium. You've got a reaction rate in one direction equal to the reaction rate in the opposite. And the concentrations don't change over time, even though there's a lot of water, a lot more liquid water than there is gaseous water. Another way to think of this is compare and contrast it with the way we've been thinking about reactions to this point. So most reactions, as we know, will stop at some point because reactants are consumed. And then, of course, the reaction shuts down if a reactant is missing. But sometimes reactions stop, and notice that's kind of shown in quotation marks for a reason, because they don't really stop at equilibrium. I'll show you what I mean in a little bit. Some reactions stop because equilibrium is reached. Okay. Now, this state of a dynamic equilibrium, again, is when the forward reaction rate is equal to the reverse reaction rate. I like to think of it as this. Imagine we have two islands. So think of dynamic equilibrium as traffic on a bridge that connects two islands. So here's my two islands. You can think of one as a highly dense, very populated island, 1 million people. This is like Manhattan Island in New York. Okay, and there's maybe right off the coast in the Hudson River is a tiny little island. There actually is one called Roosevelt Island that has a few high rises, but it has lots of open space and parks and no cars. Oh, at least it used to have no cars. It used to be connected by almost like a ski lift, a tramway. Now there are some cars. Nonetheless, it's got a much smaller population. Now, this is a small bridge, and let's say at its highest capacity, it can take 10 cars, that's a C for cars, per minute in the forward direction, and it can also take 10 cars per minute in the reverse direction, right here. Now, that's at rush hour when the bridge is maxed out. And you can see if you've got 10 leaving and going from the small island to the highly populated island, but at the same rate, 10 people or 10 cars going from the highly populated to the small, that over time, the populations don't change. And this is the idea behind equilibrium, that the concentrations do not have to be equal. As long as the reaction rates are equal in the forward and reverse directions, the concentrations can be very different, but they don't change with time. So that's important to write down. First of all, at equilibrium, again, the products and reactants don't have to have equal concentrations. And second of all, those concentrations don't change over time as long as the forward rate is equal to the reverse rate. So that's a critical concept. The other idea that's important to equilibrium is how it is approached over time. So we're going to use this reaction right here, the reaction of water vapor and carbon monoxide gas, which will form hydrogen gas and carbon dioxide. And notice it's in a closed container. It's an equilibrium system that is set up. Let's start with a system with just the reactants in it. So shown here in this jar are water molecules, there's the Mickey Mouse shape, and carbon monoxide. And then as the reaction proceeds, you can see we begin to accumulate some of the hydrogen gas, which are the small diatomics, and the carbon dioxide. And at the same time, however, we diminish the amount of original reactants because they're being consumed to create the product. Eventually, a system gets set up where these reactants and products stop changing with time. So look at the reaction diagram. The reaction diagram is not an energy diagram, it's a concentration diagram. Nonetheless, what's shown is reaction rates. Okay. And notice at the very beginning we have nothing but pure reactants. And so the forward reaction rate is very fast, very high. The reverse reaction rate is 0. Because, you know, there's no products there yet. We haven't made any products. All we have are the original reactants, H2O and carbon monoxide. Now, as those reactants start to form products, their concentration decreases, so the reaction rate decreases. And as the products begin to form, the reaction rate, the reverse reaction rate from products back to reactants increases with time as those product concentration increase. And eventually, here's the important part, the forward and reverse reaction rates become equal. And at this point, notice the concentrations are not changing with time, but are instead constant. So eventually, the concentrations of products and reactants stop changing with time. That's the idea, again, of equilibrium. All right, let's scroll forward. What do we have here? Now, of course, when conditions are constant, we can easily measure concentrations of products and concentrations of reactants. You know, just pull a syringe, pull a sample of the reaction container and shoot it into a mass spectrometer, and we'll know how much of each thing is present. So we can do math. And the math is primarily about the ability to correctly calculate and construct these things called equilibrium constants, shown with the symbol K, which we've seen before. The equilibrium constant is a number that is constant, and equilibrium constants are always written this way: the concentration of products over the concentration of reactants. Remember that the brackets mean moles per liter. In the case of gases, it can mean pressure. This is sometimes called the law of mass action, or the mass action expression, products over reactants. And that number is not quite that easy to calculate. Let's consider this algebraic expression where the lowercase letters are coefficients and the uppercase letters are, molecules or atoms, reactants of some sort. Okay. The law of mass action, is actually written like this. It's simply a ratio of products to reactants, but we write it with those coefficients as exponents. So it looks like this. A little more complicated when it's not one-to-one stoichiometric ratios. So it's simply a ratio of how much product is there, C and D. Let me scroll back up to that algebraic expression. Those are my products, C and D, with coefficients as exponents, over reactants. So it's simply a ratio with some exponents. Makes it a little tricky, but it's not terrible. Now, it's unitless. There's no moles per liter to worry about or atmospheres for pressure, because if we had exponents in there, moles squared per liter cubed. Remember, liter is a volume, so to have a cubic volume is a weird idea. So instead, the units are ignored. They're meaningless. And this, the value of the number, whether it's very large or very small, can tell us some things. And we'll learn that in a couple slides. So how do we write these? Let's practice. Why don't you take 10 seconds to write what the equilibrium constant for this expression, hydrogen gas and fluorine gas in equilibrium produce hydrogen fluoride gas. And I'll do the same thing as you write it on your paper. So remember, products over reactants. So it's going to be products, hydrogen fluoride gas squared over the reactants multiplied, which is going to be H2 times fluorine gas. And that's the correct expression. How about this one? So this is the Haber process, as you may recall. Let's once again write products over reactants with coefficients as exponents. So the product is ammonia gas squared, because it's got a coefficient, over reactants, which is nitrogen gas times hydrogen cubed. So that's what that would look like. Now this number is a constant. It's called a constant for a reason. Let's once again look at the Haber process. Please don't copy any of this if you're taking notes. Let's just use our brains and do a thought experiment here. So we've got 3 different experiments on the Haber process. The first experiment, experiment number 1, starts with in some sort of big reactor vessel. Let's say it's a big gallon size Erlenmeyer flask or something. We start with pure reactants, a mole per liter of nitrogen, mole per liter of hydrogen, no products. And we just inject those reactants and we let it run. So we started with a mole per liter of each one of those reactants. When the system has reached equilibrium, so we let it run over time at a specific temperature, that's kind of important, we get these final concentrations of both reactants and products. And we get, when we do the equilibrium constant, products over reactants with coefficients as exponents, we get this number. Okay, second experiment is exactly the opposite. No reactants at all, no nitrogen, no hydrogen, and a mole per liter of ammonia. We just inject a mole per liter of ammonia and let it run. And it decomposes, because look, this reaction does run backwards and forms some nitrogen, some hydrogen, some ammonia gas. Let's look at the third one. The third one is, all right, some random numbers. How about 2 moles per liter of nitrogen, 1 mole per liter of hydrogen? Let's throw some ammonia in there, let it run to equilibrium. And we get these numbers once the system has reached equilibrium. Well, once you plug all 3 of these scenarios into the equilibrium constant expression, guess what? You get the same number. It is a constant, okay, at that temperature. So equilibrium concentrations are not always the same. Look at these concentrations are different, okay? But the ratio of products over reactants is constant, okay? The value of K is always the same. All right, so that's important to know. All right, what's next? So, we're not going to do much more than calculating the value of K, of the equilibrium constant. What does it mean? What is the meaning behind the number? Well, remember, it's just a ratio of products over reactants. And so what if it's a really big number? What if the value of K is 10 to the 7th, and that's not unusual? Well, If it's 10 to the 7th, that means you've got 10 million times more product concentration than reactant concentration. So this is a reaction that goes to the right, that makes lots of products. And what we say in equilibrium is the forward reaction is favored. The forward reaction is favored. Now, what if it's small values of K? And that can be 10 to the negative 13th, 10 to the negative 18th. That's a really tiny number. Go right up here. If it's a really tiny number, there's hardly any product produced. An example of this might be something like a very low solubility compound. 1 in 10 billion molecules might actually dissolve. And so that's going to be, 10 to the negative 10. And that's not unheard of. By the way, let's back up. An example of a very large value of K might be a combustion reaction, where either the fuel or the oxygen gets consumed and you produce a whole lot of product with very little reactant left behind. So that'd be a big number. So here's a sort of cartoon version of the same thing. Once again, if the values of K are very large, the reaction goes nearly to completion, mostly products. If the value is very small, and that can be 10 to the negative 12th, a large one could be 10 to the 18th. Anyway, if the number is very small, the reaction hardly proceeds at all. Very, very little product again. Okay, so a little example of this. Here's the combustion of ammonia, and you can see that'd be a tough one to balance, wouldn't it? A lot of unusual coefficients there. If we write the equilibrium constant, it's going to look like this: products over exponents, products over reactants with coefficients as exponents. The value for the equilibrium constant for this reaction, a combustion reaction, is, as we'd expect, really high, 34 million, which means there's a whole lot more. For this number to be 34 million, there's a whole lot more product than reactant. So this is a reaction where the forward reaction is favored. Now, another example is boric acid, and it's a dissolution. You can see that this, by the way, boric acid is used as an ant and roach killer. It's a powder. This reaction is the dissolution, the deprotonation of the original molecule, and the K expression, the equilibrium constant, is really small, 5.3 times 10 to the negative 10, which means there's hardly any product at all. The numerator in that equilibrium constant expression is really small. So this is a very weak acid. And actually that brings to a close our discussion of equilibrium and kinetics. Next time we will discuss an important concept in equilibrium, which is called Le Chatelier's principle, which will allow us to make predictions about the behavior of systems in equilibrium. Thanks very much.